Yeah, I know what I'm saying.
Alright, today we're going to start looking at systems of equations. So, all a system is, well, there could be more than two lines, but all we're going to look at is two lines. So,
am I supposed to know this already?
You have done this before.
I just want to know if I do it real easy, I'm like, I'm genius. Well, I don't know what I'm supposed to know.
You have looked at systems of linear equations before.
See, I don't know if this also counts to me because I did not pass last year, so I don't know what I'm supposed to know.
So maybe you haven't really done it before.
I'm just a genius.
He has. We'll figure it out. Let's go.
Alright, so systems of equations. All that is I'm taking two lines, and I'm going to graph them. Okay? There's going to be a couple of different ways we're going to look at it, finding a solution to a system of equations. Okay? The first one we're going to look at is graphically, because that gives us a picture of what we're actually doing. So if I graph two lines, there's three different things that can happen. Right? The lines could intersect. If the lines intersect, I know that they have different slopes. Right? And if those lines intersect, how many points of intersection am I going to have? We want, right? If those lines have different slopes and they intersect, they're only going to intersect at one spot. Okay, that point of intersection is our solution. Right? So if I graph two lines, the solution is that point where they intersect. So, and this is going to be the most common one, right? But there are two other things that could happen. First, the lines coincide, or they're right on top of each other. In other words, it ends up being the same line. So, in that case, those two lines would have the same slope and the same y-intercept. Now, in this case, how many solutions will we have? How many times will those lines cross each other or touch each other?
One. Because they're all counted.
Infinity, right? They're going to touch each other at every single point.
Oh.
So at every single point, that'll be a solution. So we would technically say there are infinitely many solutions. The third possibility is if the lines are parallel. Now, if lines are parallel, we already talked about this idea in the last section. What's the relationship between slopes of parallel lines?
They have the same slope.
They're the same, right? So they're the same slope, but they'll have a different y-intercept. Okay, so if lines are right on top of each other, they're all the same y-intercept. If they're just parallel, they'll have a different y-intercept.
Can you say yin instead of y-intercept?
No, we're going to stick with y-intercept.
Why don't you say that? I would feel a lot happier. I would really get the concept.
Okay. Lines that are parallel will have the same slope, or different int. So, got it now?
Oh, now I understand.
Alright. So now, how many times would parallel lines cross? How many solutions would we have if I've got parallel lines? None. Yeah, exactly. They're never going to cross. If they're parallel, that's our definition of parallel. They never cross. They never touch each other. So I'm not going to have any solutions. If two lines are parallel, they're not going to cross. I'm not going to end up with any solutions. Right? So, let's try an example here of solving this system of equations graphically. So what I want to do, okay, if I'm given these two equations, I want to graph these lines. In order to graph a line, I first need to put it into slope-intercept form. What does that mean?
Y equals.
Y equals mx plus b. So I need to solve both of these equations for y. Okay? So I will subtract my x over, get negative y equals negative x plus 6. Remember, those aren't like terms, so I can't combine them. And then last step to get y by itself, I'll divide everything by negative 3. And I'll end up with y equals, what do I do with this? Negative x over negative 3. Yeah, and if I've got a negative divided by a negative, that would be positive. And now I'm actually going to do one more thing here to kind of make it look a little bit nicer. X over 3 would actually be the same as 1/3 times x. So if I do that, it's a lot easier to see what our slope of this line is. And then what's 6 over negative 3?
Negative 2.
Negative 2. So the equation of that line is y equals 1/3 x minus 2. And so we're going to do the same thing for our second one here. Solve it for y. So I'll subtract my 2x over, get negative y equals negative 2x minus 3. And now I have to get rid of that negative sign in front of the y. So I'm going to divide everything by negative 1. I will end up with y equals positive 2x plus 3. So now I just want to take both of those equations and graph them. So how would I do? How would I do that? Let's start with the 1/3 x minus 2. How do I graph that?
Because negative 2 on the y-axis.
Start at negative 2 on the y-axis. Perfect.
And then you would go up 1 and right.
Exactly.
Wow, good job, Lawrence.
So up 1
Don't let
and right
anybody hold you back.
3. Right? I could also go down 1, left 3, and then sketch that line.
You can just do a straight edge.
Yeah. Straight edge would be a good idea.
Maybe.
Watch out.
How about this one? We want to plot y equals 2x plus 3. How do I graph that one? How do I graph y equals 2x plus 3?
The y on the y-axis is 3.
Yeah, so start at 3 on the y-axis.
And you can go up to a 1 or down to.
Right, so we would either go up to right 1, which will kind of be off our graph here, or I can go down to left 1, down to left 1, down to left 1. Right? Then sketch out that line. So now that we have this system of equations graphed, we can see what our solution is. Remember, the solution is the point of intersection, okay, the place where these lines intersect. So my solution should always be a coordinate point. Right? So if you want to make a note of that, that might be a good idea. Solution, whenever we have one solution, is a coordinate point. So what is my solution to this system of equations?
Negative 3.
Negative 3. At this point of intersection right here. So,
Coordinate point means like a whole.
like an x and a y. So like this is a coordinate.
I think like it has to be like one of the lines.
Where they intersect.
Are you saying like that's a coordinate point and that's not?
Yeah.
Okay, so that's not entirely true.
Oh no! Now there's gonna be some graphics.
So that's why graphing isn't always the best method to find the solution.
I don't remember. I remember Brian's thing. A whole bunch of other stuff I don't know.
Right? But for right now, we're going to find our solutions graphically. Right? So let's jump down here and try a couple of these. Right? So we're just going to take maybe 10 minutes here. Okay, and you guys practice these ones down here. Alright, so remember, the first thing you need to do is solve each of these for y.
Can I go to the back?
So solve each of these equations for y, graph them, and figure out where they intersect. Okay, now, it is possible that they won't intersect, remember. Or it's also possible that they'll be the exact same line. Okay. Most of them, though, you'll get 1 point of intersection, but not all of them. Okay, so start by solving each equation for y, and then graph them, see where or if they intersect. Now, if you did get to number 4, or 5, or 6 down here, number 4 ends up being one that does have a single solution. These two lines cross at the point 2, 1. Number 5 ends up being another one where the lines sit right on top of each other. And then number 6, we have one solution again. The lines crossed at the point 2, 4. Questions on solving a system graphically?
What is consistent?
We're not going to worry about those things.
I just went up because I wrote parallel and all that. And oh boy, got some pink ones up there. Yeah, those two are right on the money on that good.
What?
Those two, 4 and 6.
I put those.
Oh. I was up there.
All right, so we are going to look at one other way to solve systems today. Okay, the second method that we're going to look at is substitution. Right? We're going to do this without a graph. This is going to be all algebra to solve a system. So let's take this system right here, 2x minus y equals 9, and x plus 3y equals negative 6. To use substitution.
Oh, wait a second. Isn't this like a really, like, it's just really cute? Isn't there like,
Is this the one with
you
the
have to
three
keep
step
plugging in a whole bunch of stuff?
With the 3-step equation?
Yeah.
Yeah, I mean, there are 3 different things that we need to go through here.
Okay, that's good.
Okay, so the first thing I want to do, I can pick either equation and solve it for either variable. Okay, now, sometimes it's going to be easier to solve for one thing or the other. In this first equation here, I've got 2x minus y. In the second equation, I've got an x plus a 3y. Now, it does not matter which one you choose. You can solve for any of these variables. But which one looks like it might be the easiest to solve for?
The bottom one.
The bottom one for which variable?
X.
Yeah, because there's only one thing I would have to do to get x by itself. Right? So I'm going to take that equation and solve it for x. So x plus 3y equals negative 6. To solve it for x, I would just subtract this 3y over. And I end up with x equals negative 3y minus 6. Once I have one of the equations solved for one of the variables, scribble that piece out right there. So I'm going to take this expression, okay, this negative 3y minus 6, and plug it in for x in the other equation. Okay? Just pull that out as well.
You just keep, and once you have that variable, then you solve the other one. You just keep going back and forth to the other one.
Right. But we only would have to go back once to plug it back in. Right? So what we're going to do, so in my other equation, the 2x minus y equals 9, I'm going to take this and put it in place of x because I solved this equation for x. I have an expression that's saying x is equal to this, so I can put this in place of x. So I'm going to say 2 times negative 3y minus 6 minus y equals 9. Now I have an equation that only has one variable in it that I can solve. And we know how to solve things like this. So I would distribute this 2 through. So negative 6y minus 12 minus y equals 9. I can combine these like terms over here. Negative 6y minus y would get me negative 7y minus 12 equals 9. And I want to get y by itself, so I will add the 12 over. Get negative 7y equals 21. Divide both sides by negative 7. We end up with y equals negative 3. So that's half of my answer. Remember, our final answer should be a coordinate point. I should have an x value and a y value. We solved for y. Okay, so now what I want to do is take this answer and plug it back into one of the equations. Okay, it doesn't matter which one I choose. I can take this value and plug it in for either of these values. Okay. You have a preference? First equation or second equation?
Second.
Second? Alright. Let's plug it into the second one then. So I'm going to take this value and plug it in for y right there. So I'm going to have x plus 3 times negative 3 equals negative 6.
What? No, I understand what you're saying. I'm just doing one.
Y multiplied. Well, did that first part there.
Oh, so is that all right there in front of that?
Yeah, we're all
Okay.
still all the first problem.
Is that supposed to write all over the board for you?
It's your notes. It's up to you how you want to write this.
Well,
So 3 times negative 3 is negative 9. Add the 9 over. End up with x equals positive 3. So now my final answer, I have my x coordinate and I have my y coordinate. My final answer is the coordinate points 3, negative 3. That is the point where these two lines would intersect. If I graphed them, like what we did on the other side of the notes, I would find that these lines intersect at 3, negative 3. Okay, so your final answer should be a coordinate point, unless, of course, they end up being the same line or parallel. We okay with something like that? Do we want to do another one together?
no, it's almost time to go. We better.
We've got time to do another one together.
Fach, no.
All right. So let's take a look at number 1 here. Okay. So first thing I want to do is choose one of the equations to solve for one of the variables. Which one looks like it would probably be the easiest?
Top one.
Top one for x or y? Y. It would probably be easiest to solve this first one for y. So to do that, I would just subtract the 3x over. Right? So minus 3x, we get y equals negative 3x plus 7. So now what I can do is take this expression and plug it in for y in my other equation. Right? I solved for y, so I want to take this and plug it in place of y in my other equation. So that will look like this. 4x plus 2 times what we just solved, negative 3x plus 7, equals 16. Distribute this 2 through. We get 4x minus 6x plus 14 equals 16. Combine my like terms here. So 4x minus 2x, or I'm sorry, 4x minus 6x is negative 2x. Plus 14 equals 16. Get this 14 over. So subtract that 14. Divide both sides by this negative 2. And we end up with x equals negative 1. So remember, that's only half of my answer. What do I need to do now to get my other half of the answer? get the y. So how do I get the y?
Just plug x back into to the math. You do the same one.
It doesn't matter. You can use either of the two equations.
Put the x in, and now you have to go find the y.
Right. So I'm going to take this value for x and plug it into one of the equations. I'll use the first one since it's got smaller numbers. So I'm going to plug -1 in place of x. So 3 times -1 is -3 plus y equals 7. Then all I have to do to divide by itself is add that 3 over. I get y equals 10. So what is my final answer then?
Yeah, plug it in.
Well, we have our x and y.
It's -1.
So my final answer is the coordinate point, -1, 10. Okay. Remember, when you're writing the coordinate point, you always put the x coordinate first, y coordinate second.
And you can just plug them in to find out if they're right.
Yeah, exactly. If you wanted to double check, you could plug -110 into both of these and make sure that you get something that works. Okay. Any questions?
Maybe
What's stressing you?
Add it out.
Alright. So